So let's go ahead and get started. Right now, last class we left off talking about the orbital hybridization for single bonds. In particular, we looked at just methane. You can actually do the same thing with ethane, which is being C2H6. It's just that one of the bonds, instead of having a carbon with 4 hydrogens, it's going to be a carbon to a carbon. Okay. But otherwise, on your own, you can sit down and work out or look at the examples on your own of ethane. But now we're going to go to ethene, which is also called an ethylene group. And this is what ethene looks like when we draw it out. Oh, whoops. If I draw it all the way out. This is an alkene, and eth means how many carbons? In case it's not obvious. 2. Remember, if we can say, kind of memorize, it's meth, eth, pro, bute, pent, hex, hept, oct, non, and dec. By the way, then even going to 20 is not too bad. It's undec, dodec, tridec, tetradec, pentadec, things like that. But it literally means, like, for example, 1 plus 10, so on and so forth. But I always make you memorize 1 through 10. Okay, so here, let me change the color on one of these so that way it makes it a little bit. Here we go. And here we go. All right. So we're going to start with the light-colored C and talk about its orbital hybridization. And so remember, this is that C. And not to skip any steps once again, how many valence electrons did it have? 4. Oh, the pen is sticking right now. Okay, and so we have 1, 2, and then where did the last 2 go? Px and Py. And so, once again, this is only the valence electron, so this would be 2s2, 2p2, which technically is a 2px and 2py. We add just a little bit of energy. And because right now, if we look at just this yellow, so we're just looking at the yellow carbon. So it has 2 hydrogens hanging off of it, and then it's got a bond to a carbon. So we have enough holes there, enough hotel rooms, if you want to think of it that way, in order for that to bind and to be correct. However, or I should say for it to bind, for the electrons to come in. However, we know that that's not correct in the sense that we have that 2, that an empty one, that if you put the 2 hydrogens in there together, they're actually not making any bonds with any covalent bonds to that carbon, because it's completely just their electrons. And so what we're going to do is you just have to add a small amount of energy, and we can easily pump one of those electrons from that carbon from the 2s2, to the 2s, to the 2pz. Okay, and so not a big, this is a little bit of E, that's supposed to be an E. E. All right, so a little bit of energy, and then we'll pop that up. However, we know that this is still not right, because otherwise we're going to have one bond that's really short and strong, or stronger, and then 3 bonds that would be weaker because they're longer, they're higher in energy. Okay. And so what did we do in the example with methane, whenever you have 4 things off? How do we make 4 equal bonds? We hybridized, we mixed it. However, if we look back here at this carbon in this example, and we go back to Sesame Street with like the count, we have 1, 2, 3 things hanging off that carbon. So we don't need to hybridize 3 of the orbitals. So we pick these 3, we hybridize. So that also takes some energy. So instead of having an s with 3 p orbitals, we're going to have 3 of the sp2 orbitals. All three of those, and just for space, I didn't put it down, but there's an sp2 under each one of those. And we still have one p left. And so in this light color, from the light colored carbon, we still have its 4 electrons. So now we have to add in the bonds. Right? I apologize if I don't keep the colors correct. I will try my best. So how many hydrogens do we have that we're bonding? 2. And will they be in the sp2 orbitals, or is it going to be crammed into that p? It's the sp2. So we have a hydrogen and a hydrogen. Whoops, it's supposed to be hydrogen. All right. Then what else is in the other sp2? That carbon. Right? So we've got the sp2s taken care of. So what is that p? There's a p that's left over there by itself. First of all, it's not happy, because if we left this alone, there's 7 electrons there. There's not that 8th one going around, to make that full octet. So where does that other p come from? It's the double bond. So now, this is going to be a little, let me change this color. We have to remember we've got 2 carbons. Right now we only do that for 1 carbon. All right. And so if I did another one, which would make it really complicated, that red? That red carbon, it's going to have its 2 hydrogens. It's going to be sp2 as well. And then it's going to be linked to the light colored carbon in the 3rd sp2, but it's going to have an empty p. So the 2, or I should say half empty p, the 2 half empty p's come together to make a whole p. So let me draw what that looks like. We just have to remember all of this is multiplied by 2. You have to multiply all of this by 2 because there are 2 carbons. So what does this look like? And I'm going to attempt to draw this well. We have, what's the shape of the p orbital? It's a dumbbell. So right here's that carbon, that light colored carbon. And I'm going to draw that was its p. Let me go to just a slightly darker shade for its sp2 orbitals. That's the hydrogen. Oh, this is one of my better ones. I have to definitely post this one online because usually it turns out a lot worse than this. Okay. With its C. Whoa. And its hydrogens. Okay. Unfortunately, this app doesn't have the little highlight that I can do. All right, so right here, we have the 2 C's with their dumbbell P. Remember, each P is a dumbbell, but there's only 1 electron, and this one from the light colored C and 1 electron from that. And they have this side-by-side overlap. Okay, so that's why the little 2 dumbbells are kind of mixing. All right. Then we have the hybridized orbitals, which come out like this and like this. So if you think about this in 3 dimensions, which it's really hard for me to draw this in 3 dimensions. 3 dimensions, what this means is, for example, these lobes of the dumbbells are coming out towards us. These are going away from us. So it's coming out to the plane of the wall or room. That one's going back into the room next door. These 3, the light colored, and those are the sp2s. So if we just look at the angle, that's why this 1, 2, 3, those are all in the plane. That's why it's called trigonal planar. The angle between this hydrogen and this hydrogen is how many degrees? 120. It's 120 degrees because it makes a circle. See, there's a circle here. So that circle is 120 degrees. We have one there, and one there. And likewise for the other carbon as well. However, this lobe, these are coming out towards us. These are going away from us. So that would be coming out towards like going to hit you in the head, and the other two are going away. So what makes that special is that lone p electron that we talked about here, and there's one from each, that's what makes a pi bond. No, p is pi. That's what makes the pi bond. And so pi bonds are just unhybridized p orbitals that were left over from the orbital hybridization. Right, so now let's try to do a triple bond. So here in the triple bond part, this would be acetylene, which is also called ethine. Oh. Hopefully you kind of get an idea of where this is going. We have the yellow C and the red C. And so here, 1, 2, 3, 4. This is where I've already added some of the energy, but before I've hybridized. Okay, so I've already skipped the first step. But if we look at that light-colored C, how many things is it bonded to? How many orbitals do we need to hybridize now? We have an S, and these are all three of these are P's. How many of them do we need to hybridize? How many things are hanging off that carbon? Just 2. The, what is that, red carbon, and then the hydrogen. And so that means that it just needs to make sigma bonds to 2 things. And so we're just going to hybridize these 2. So you add a little bit of energy. Now it's going to look even fatter. So normally a regular S orbital looks like a sphere. Regular p orbital looks like a dumbbell. When it was sp3, it looked more dumbbell. It was 75% dumbbell and just 25% sphere. Well, now that's an SP, it's going to be 50-50. So these are really short, squatty, and the PowerPoint and the book does a much better job of showing the actual structure of what it looks like than I would. But literally, it's halfway up in energy, and then we still have 2 P's left over. So just looking at it from the light-colored carbon, which orbital is that hydrogen going to be bound to? An sp. And so remember, if we want to, we can put it here. This is an sp. This one's also an sp. But what's bound in there? That carbon. Okay. So, what's in the other 2? What's in these 2 right here? Those are going to be the 2 pi bonds. And so you probably, I don't remember if I taught this or if you learned in Gen Chem 2, but you probably learned, I'm going to redraw that first one. I'm going to blow this up so I can draw it a little bit better right on them. When you learned these and you had to count like the number of sigma bonds versus pi bonds, you can say, oh, that one's a sigma and that one's a sigma. And we would say one of these, and a lot of times they would say, oh, this one's a sigma, and then this is a pi, and this is a pi. It doesn't really matter of that three. One of them was a sigma, and the other two are pi's. This is actually the reason why we say that. You can see all the orbitals that are hybridized are sigmas. So we have the one of the hydrogen, which is a sigma. We got the one between the carbons as a sigma, but the other two that's left over between the carbons are pi bonds. Okay? So that means that's how we get a triple bond. And just notice for the, what is that, red colored carbon, instead of its hydrogen, which is that other color, not the blue one, but the other color one, it's going to be its own sp. So if we draw this one's really difficult to draw. But if we try to draw this one, I will attempt. I can't guarantee it's going to be color-coded whatsoever. In fact, I'm not going to make it color-coded because it's going to mess me up since I can't tell them apart. Okay, those are easy. That's the easy part to draw. And then we have, I will change this color to show the triple bond. And there's supposed to be overlap between those lobes. I already have a video out there that's just a tutorial on how to do alkyne. Just alkyne, which I don't have it on the MyFire page yet, but it's on the website for the tutorials for the website on the blog. Feel free to look it up because I did a much better job drawing it there. But that's how we get, it's two sets of dumbbells that are overlapping. And we have to remember this is all in 3 dimensions. But the overall molecule, like if we look from hydrogen, we measure the angle from hydrogen to carbon to carbon to hydrogen, it's 180 degrees because it's linear. So that's how we get a triple bond. Triple bond is formed between 2 leftover p's, which make 2 pi bonds, and then you have that one that's the sigma bond. Okay.